welcome to Life in Biology. I'm Dr. Joel Graff. This is another lecture from my 100 level biology class. The first lecture we did an intro to chemistry. The next lecture was an intro to organic chemistry. And we're going to continue on with organic chemistry and round it back to just regular chemistry over the course of the first 4 videos. I'm calling this video number 2 because the very first video was on the first day and it was not a very long lecture, so I just gave that lecture number 0. So just to bring us back into talking about hydrocarbons, here's an example of a hydrocarbon. It's ethane. Eth means that there are 2 carbons involved, and ane means that there's single carbons within this, or single bonds within the carbon chain, the growing carbon chain, although I don't know if you can call 2 carbons a chain yet. But then you've got hydrogens filling out the around it, and although this molecule was written or drawn on a 2-dimensional surface, it's actually 3 dimensions. Some of these hydrogens might be kind of angling out towards us, and some of those hydrogens might be angling into the screen. So you just have to kind of imagine this has kind of two triangular ends to this molecule. Anyway, after ethane, after that 3D molecule, we will see that you can have a double bond between those carbons. Again, carbons like to form 4 bonds, so if you have 2 bonds between the carbons, then this carbon only needs to make 2 more have 2 more shared electrons, covalent bonds, and so there's only 2 more hydrogens needed at this end of the molecule and 2 hydrogens needed at this end. So that was ethane, and this one's ethene. Now, whereas the hydrogens were all kind of in 3 dimensions here, and they could spin around to some degree, this double bond creates a kind of an interaction between these carbons where they can't twist around each other. So the carbons are not going to be able to twist, and then you've got some bonds going off to the right, and then you've got a bond going up to this hydrogen and a bond going down to that hydrogen. Those hydrogens are going to be trying to distance themselves out so that we kind of have even spacing, but for the 2 hydrogens and the carbon around this central carbon here. Same thing here. And so this molecule is actually just 2-dimensional, and it's planar. These hydrogens don't actually come in or out of the sheet. It's nice and parallel with the 2 dimensions of your screen that you're looking at right now. So that was ethene. And then of course you could even push your luck and go to a triple bond between this carbon and this carbon. Because there's 3 bonds between the carbons, each carbon here only wants to do 1 more covalent bond, and so we've gone down to C2H2. This was C2H4, and this is C2H6. Those molecules, the hydrogen is going to try to get as far away from the carbon over here as possible. So that's a straight line. Same thing here. So those 4 atoms would be lined up essentially in a straight line, and so it's going to be more like 1-dimensional. It's going to be linear. Now, because of the triple bond, we can call it ethine, Y-N-E, and another name for this molecule is acetylene, but that's kind of the colloquial name for it, whereas ethine is the name that you would give it if you're following all the nomenclature rules like we're trying to do in this class. Next up, we've got branched chains. So far we've drawn carbon chains that are more or less linear. You've got carbon 1, then carbon 2, then carbon 3, then carbon 4. There's some zigzag to it, but they're essentially in a row. And then the hydrogens, there would be 3 hydrogens associated with each of the end ones, and then a couple hydrogens located here. But overall, you'd have generally a fairly linear molecule. However, you could rearrange those 4 carbons and the 10 hydrogens so that you have a central carbon here that has 3 CH3 groups. We're going to learn later on that's called a methyl, and then it has another hydrogen. And so this molecule here has the same chemical formula as this molecule here. This one was called butane. Molecules that have slightly different shape but the same formula are called isomers. So if this one was butane, we're going to call this one isobutane. Up next, in addition to branching your hydrocarbon chains, you can also have the hydrocarbon chains form round or circles. And so in the case of hexane, you have 1, 2, 3, 4, 5, 6 carbons. There are 14 hydrogens all around this that I didn't draw in. And those 6 carbons could meet up one end to the other and form a 6-carbon ring, which is what we have here. I started drawing out the hydrogens here, a hydrogen here and a hydrogen here, there and there. And then I got lazy, so I just switched from writing a carbon and showing 2 different hydrogens to just writing CH2, but they're the same idea here. And this molecule is called cyclohexane. Now, if you start adding in 1 or 2 or 3 double bonds, you could eventually get to this molecule here, which is an alternating double bonds, and in fact it's more like there's 1.5 bonds between each of these because the electrons are floating around those carbons so much. And then you've got just 6 hydrogens here because each carbon has a double bond going in one direction to another carbon and a single bond going to another carbon, so you only have to add in one more molecule, and that's hydrogen. So this one was C6H14, excuse me. This one was C6H12 because each carbon had 2 hydrogens with it, and each carbon here has 1 hydrogen, so it's C6H6. And if you want to be lazy or use shorthand, I should quit saying lazy. This is the shorthand. You're being efficient. You could draw a hexagon with a circle in the middle to indicate that you have what is known as a benzene ring. Moving on to functional groups. What I've drawn on the left here is an amino acid. This particular amino acid is known as cysteine. And we will take a look at several different amino acids later on, but the interesting thing about these molecules like this is that although they look complex to begin with, if you aren't used to looking at molecules, once you learn some of the functional groups, which are like a collection of molecules or a collection of atoms, you can see that you can just start adding on functional groups to things to change them. So I started putting all these dots around the different functional groups. There's a C double bonded to an O. There's a C with an O and then an H. There's a nitrogen with a couple hydrogens. There's the sulfur group with a hydrogen. So these are each functional groups. And I want to start off talking about the carboxyl, which is this entire carbon double bonded to a carbon, carbon with an O and an H. That's the carboxyl group. And the R here is just meant to be anything. And so I had all sorts of molecules over here to the left of this carbon, but we could just summarize a carboxyl group by writing R and then just saying you have this COOH functional group there. Over here we've got a nitrogen with a couple hydrogens stuck onto this central carbon, and again we can use an R to represent the carbon and all the molecules, or excuse me, all the atoms on the right side of this molecule. And so you have an R, which could be anything, and then an N with 2 hydrogens, and that's an amino group. So we've learned 2 functional groups so far, a carboxyl group and an amino group. The carboxyl group is fairly complex, but it's actually 2 simpler functional groups kind of combined. So here we have what's called a hydroxyl group, which is an R with an O and an H, oxygen and hydrogen. And then over here we've got a carbonyl group, and we've got R group number 1 connected to a carbon, and then R group number 2. So really what makes up this functional group is having a carbon with a double bonded to an oxygen. The things on either side of the carbon here could be anything. So if we take a look at what a carbonyl is, that's a double bonded oxygen, we can see that it's located in the part carboxyl group here. And over here we've got anything connected with an O and an H on it. So here's the carbon, which is the R, and then here we've got the O and the H. So if you take a carbonyl group and you combine it with a hydroxyl group, you end up with a carboxyl group. And so you take the beginning of carbonyl, the end of hydroxyl, and you end up with carboxyl. Next up, we've got a sulfhydryl group. Sulfur, we don't talk about that too much. It's below the oxygen. It's in the same group on the periodic table as oxygen. We know that oxygen likes to form two covalent bonds. And so here, it's not too surprising that if you have an R group and then an S, a sulfur, connected to it, the sulfur is only going to want to form one more hydrogen bond. So sulfhydryl, sulfur, hydrogen, sulfhydryl. Those groups are also called thiols. Okay, just a couple more to go. First off, we've got a methyl group. Before the sulfhydryl group was on here, maybe it was a hydrogen, and so then it would be a CH3. Here I was kind of lazy with my drawing. It should be a C and then an H up, H down, H to the right, or CH3 like that, all in one go is kind of a shorter version of writing that. But that's a methyl group, and that's not too surprising because we knew methane, meth meant one carbon, and then there's a bunch of hydrogens around that one carbon when we're dealing with methane. So methyl group is kind of like methane. It's just this fourth covalent bond is to some sort of R group instead of to just hydrogen. And finally, we've got a fairly complex functional group here called a phosphate. The R group here is connected to this combination of phosphorus and oxygen and hydrogen. If we notice, there's a phosphorus in the middle and there's an oxygen in each direction from that phosphorus. One of those oxygens is a double bonded oxygen. Another oxygen is what was connecting to the R group. So in both of those cases, they have two covalent bonds and they're fine. If phosphate's connected to oxygen with one covalent bond, then the oxygen will want to connect to a hydrogen with one covalent bond. This oxygen wants to connect to a hydrogen with one covalent bond as well. So those are the functional groups that we're going to learn this semester. And let's move on. In this one, we have charged functional groups. So amino, we drew that earlier, R and N with two hydrogens. Carboxyl, we took quite a bit of time talking about that because that was the carbonyl group mixed with the hydroxyl group. And then we got to the phosphate. Now, important to point out is that under biological pH, these functional groups will look a little bit different. For example, there's usually a proton floating around in water that this nitrogen group this amino group would pick up. If it picks up a proton, the proton had a positive charge. So now this nitrogen has 3 bonds to hydrogens, and because that hydrogen had a plus charge, this whole group will have, in general, a charge of +1. Carboxyl, we're going to go the other way, where this was a +1 charge, carboxyl will be a negative charge. So where did that hydrogen come from? Well, it might have come from a carboxyl group. The carboxyl group has COOH on it, but under biological pH, the oxygens here would be too greedy for electrons, and this hydrogen would lose its grasp, and that sharing that was going on between the oxygen and the hydrogen here, the oxygen would win that tug-of-war battle. The hydrogen proton would float off, so just a proton would float off, and because you lost a positive charge and that the electron stayed here, then this group has a charge of -1. And then finally we have phosphates, and I think we can talk about this a little bit more quickly. Just like this hydroxyl group lost its hydrogen, this phosphate group has a couple of hydroxyl groups on it, and they both lose their hydrogen, and so you end up with a functional group that has a net charge of -2. So +1, -1, -2. So those charged functional groups, they're going to be eager to do some chemical bonds with other things because they're charged. So we'll take a look at that as time goes on. Next up, we have aspartate. So you might notice that the top half of my amino acid here is the exact same as what we saw before. It's just the bottom half, and we call that the R group, is different. So this is what an aspartate looks like. We've got amino group, carboxyl group, and another carboxyl group. And under biological pH, aspartic acid would pick up a proton for this amino group, it would lose a proton for this carboxyl group, and it would lose yet another proton for this carboxyl group. So you gained 1 plus charge but lost 2, so your overall charge for an aspartic acid is -1. Next up, when we are dealing with macromolecules, we're usually working with molecules that are considered polymers. Polymer, poly means many, and mer means part. So you could have a monomer, which means one part, a dimer, di for 2, mer for parts, tri, 3, mer, parts, tetramer, 4 parts, oligomer, several parts. So oligo is kind of a weird one. It just means several or a few. And then polymer means many. So if we wanted to draw out these molecules, this first one would have 1 part, shown in blue. The second one, a dimer, would have 2 blue parts connected with a covalent bond. A trimer would have 3 parts connected with covalent bonds. And a tetramer would have 4 parts connected with covalent bonds. So amino acids and nucleotides are good examples of molecules that are just going to keep getting longer and longer, and you just keep adding parts to one end. But how do you add parts? So that involves creating a chemical bond, and chemical bonds are created and broken during a chemical reaction. So chemical reactions involve forming and breaking bonds. So we're going to talk about an example where we have a trimer and a monomer, and we're going to combine those together. A 3-part plus a 1 part equals a 4 part. And the thing that also happens is that this reaction is considered a condensation or a dehydration reaction. And so a water molecule comes out. Where did the 2 hydrogens and the 1 oxygen come from? You had a hydrogen here and a couple oxygen, or an oxygen and a hydrogen here, and those could be put together to make your typical water molecule. This reaction is reversible, so I should have had arrows on this end. You can take a tetramer, break a bond between the 3rd and 4th pieces, and end up with a trimer and a monomer. So if the reaction goes in a direction that forms bonds, we are going to be doing condensation and dehydration reactions. And if we're going to break some bonds, we're going to end up doing what is called a hydrolysis reaction. Hydro for water, and lysis, water to break. And that looks like the last slide for this lecture.